of lectures. We are talking about line integrals. We are supposed to cover at least 3 sections tonight and hopefully a little bit tomorrow, which is what we need to get through. The first topic tonight is line integrals 14.2. What are the line integrals? What do they compute? How they work? Before we even go into it, you did the class prep, you saw that parametrization is playing a key role in getting all of this together. So you can expect parametrization in every single problem. Also, what are these integrals computing? Well, if you look around yourself, you see these walls. Each wall is a rectangle, and it's fairly easy to compute the area of each one of these rectangles. We just measure length and height, we're done, right? Now imagine that you have a curtain. You know, the curtain for the windows that it hangs, and it's wavy. Now, obviously, if you want to calculate the area, you will stretch that, and you will measure, and you will get the rectangle, and so on. But let's say it's made out of steel, and you can't. All right? I don't know if you've ever seen the steel curtains or not, but they don't exist. And what are you computing technically? The line integral is going to be the area of that curtain, and C will be the curve on which that curtain arises from. So technically, if you have some kind of a space x, y, z, and you have some kind of curve here, we call that curve C. This curtain, which is wavy, I'm not sure how to, draw this perfectly, but this over here is going to be the area of the curtain. And the line C is going to be parametricized through whatever parameters we have. So this line C will be given as x being some function, I don't know, g of t, and y some age of t. So we are getting, in this case, we are getting, let me just make sure that the stream is going, it's somewhat healthy. So now what are we having here? Well, we're going to have exactly the same idea as we had in calculus 1 for Riemann integral. We are going to make all of those delta, but these are going to be our delta t's now, because everything is parametricized in terms of parameter t. And what you do is you multiply them all together with the height of the function, and you get exactly the same thing like in calculus 1, the Riemann integral. So the derivation area will be approximated by summation k goes from 1 to some n, finite n, because we have a finite amount of these rectangles before we send n to infinity. We have our function f, which is parametricized in terms of the two functions x of t and y of t, which are those g of t and h of t. So those are multiplied by all the delta t's. So now you do the same trick, which is the n goes to infinity. So if n goes to infinity, we know that delta was always b minus a over n. So as soon as you send n to infinity, delta must go to 0 because you are dividing the finite number with the infinity. And as soon as all of that happens, we get our definition for scalar line integral in the plane. And that definition is that, so we have the C is going to be our R. Not sure why the book likes this S so much, so let's use it. Parametricized in terms of the arc length S. And then we're going to get the line integral of F. So it's going to be integral over the curve C. Oh, by the way, this curve needs to be smooth, which means it does not have any of those kinks like this or like that. It's smooth. It's differentiable everywhere. So we have f of x s, y of s, ds is equal to the limit, come on, as n goes to infinity of the summation f of x of s, y of s, those are the parametricized values, times the delta s. Okay. So this is the definition. We are obviously not going to do Riemann integral every time we need to compute. We have our theorem, which will convert all of this into the integral that we know how to use. So let's immediately go with the theorem, and this is what we are going to use. So integral of f ds, which is the line integral, is going to be, so a to b, f x parametricized t, y parametricized t, times r prime of t, the magnitude, dt. And now you can write the r prime, spell it out. Which is the square root of x prime of t squared plus y prime of t squared, because this is just computing the magnitude, dt. So this is what we are actually using to compute line integrals. So let's immediately look at the example of this. So what it says, average temperature on a circle. The temperature on a circular plate R, so circular plate R is given as all x and y's such that we're looking at the unit disk, and the temperature is given as 100 x squared plus y squared. So now what do we have? Well, first we have a curve. Curve C, over which we are computing the line integral. is going to be given as what? Remember that x is r sine, x is r cosine theta, and y is r sine theta. So we're going to have that curve C is all of the points x, y, such that we have x is equal to r squared cosine squared, but then r is 1, so we just have cosine squared there, t, as a parameter. And then y is sine squared t. Again, radius is 1, so since radius is 1, r squared, 1 squared is 1, so we don't have to write it. And we also have that t goes from 0 to 2 pi, but we have to put the square root there because we have cosine and sine, both are squared. So this is a parametrization that we can use for our curve C. What are you looking for? You're looking for the average temperature along that disk. Exactly. So what are we going to do now? Well, let's figure out first the r prime, because we can do that. So what's r prime? Well, first, what's r? R is your parametrization. Parametrization is given as cosine squared t sine squared t. So what's r prime then? Anyone? It is 2 cosine t sine t and the negative in front, right? And what else? 2 cosine, no, 2 sine, yeah, 2 sine t cosine t. And then we square them and we add them. So the magnitude is going to be, well, can we write this as 2 sine 2t? So this is sine 2t, square that is going to be sine squared 2t, and then plus another sine squared 2t, which gives us square root of 2 sine squared 2t. When you take a square root, you get root 2 sine 2t. How did they do here? All right, so now what we do? Yeah, but I don't like it. Negative 2 squared is 4. Oh. Negative 2 squared is 4. Oh no, this was supposed to have another 2 out front, but something is off here because let me just see if I copy the problem right, because I don't like the way it's x squared plus y squared less than 1. Temperature is 100, x squared plus y. Okay, so here's the first mistake in copying the problem. Maybe there is more. This term in the temperature is supposed to be 2y squared. 2y squared. And then, yeah, there we go. Squares are in the wrong spot. I should have caught that. So these squares here, guys, I have cosine squared t is supposed to be cosine t squared. Because if you have a square root of 2 pi over here, you put the 2 pi square here, that one, not the cosine of it. All right. So now we got to switch this real quick. Which changes the derivative and changes the calculation here. We'll live.
So they're going to give us the curve to see?
Yes, the curve is given. Well, unless it's something easy like a linear line or something that you can quickly parametrize. Circles you can parametrize, lines you can parametrize, even the ellipse, but you don't want to do ellipse in integral. So there are a few things that you can do on your own. All right. So let's differentiate this. I have the chain rule here, so it's going to be derivative of cosine is negative sine. So we have negative 2t sine t squared, and the derivative over here is going to be 2t cosine t squared. There we go. That's much better. So now, when we square this, we get 4t squared sine squared t squared plus 4t squared cosine squared t squared. You factor out 4t squared, and that's going to be multiplied by sine squared plus cosine squared, which is 1. So the whole thing is 2t. Much better. Now we set up our integral. The integral is going to be the integral over curve C of the temperature, ds. So 0 to square root of 2 pi, those are the limits for t. They are given to us in the upper right corner. And we take our function t, but function t has to be parametricized in terms of the parameter t. So the function is 100 times x squared, but x is given as cosine t squared, so that's cosine squared t squared. You know what? Let me write it out in a first. So x squared plus 2y squared times 2t is our r, and then dt. So at least something. And now I will just point the arrow here and say plug in. So you know you are supposed to do that. I'll pull 200 in front. The integral 0 to square root of 2 pi. And now this parenthesis here is parametrization. So look at the big pink arrow. That's where your x and y are. Okay? So x is cosine t squared, so cosine squared t squared plus 2 times sine squared t squared. And then we have times t. I kicked out 2 times 100 dt. And now we use a little bit of u sub over here, right? Because you have t squared, and then you have t outside. So we use u sub. U is equal to t squared. du is equal to 2t dt. And we can compute everything. So I'm going to steal a 2 from this. So it says 100 integral 0 to 2 pi, because when you plug in the square root here, square will kill the square root. There we go. And then I have cosine squared u plus 2 sine squared u du. Can you? But there is a 2, they're not the same, right? They have different coefficients. So you can write sine as 1, if you write cosine as 1 minus sine. Yeah. It's still quick, either way. Now we can do it now. To ease calculations, we can write cosine as 1 minus sine squared u plus 2 sine squared u du. To make this easier, we get 100, 0 to 2 pi, and this becomes 1 plus sine squared u du. Fair? Good. And then we only have to transform one of these now. So it's 100. Now observe that I will not be going back to t's because I transformed the limits already. So I'm just going to solve it in this state. 1 plus 1/2 minus 1/2 cosine 2u du. That's 3/2. So 100 3/2 u minus 1/4 sine 2u computed from 0 to 2 pi. Both of these are going to die when I plug in into sine, so all we have is 100. Well, actually, half of the 100 is 50 times 3 is 150, so 150 times 2 pi, so 300 pi, I hope, as a calculation. Check that. So half of 100 is 50 times 3 times 2 pi. Yeah, good. All right. So 300 pi. This is a standard procedure on computing the line integrals. We are going to go through this calculation one more time because I copied the problem wrong. So let's take a look at the whole calculation. So first of all, we have a disk, x squared plus y squared less equal than 1. That means that the disk is solid. It's a unit circle, and it's a disk because it's less or equal than 1. Then we have a temperature function, which is given as 100 times x squared plus 2y squared. And we also have a curve along which we want to compute the temperature. So what do? Well, we know from definition what are the components that we have to compute, like r prime. But the most important thing here is to understand that I should box this together. This is along with the limits there. This is your parametrization, and it's going to be there in every single problem. In some problems, parametrization is given to you. For some other problems, you will have to figure it out on your own. As I said, the circle as a parametrization, not a big deal. You know how to parametrize circle, r cosine theta or t or I sine t. So that's quick. Also linear line or whatever else is cheap and easy, you can pretty much parametrize quickly. If there are some crazier parametrizations that you would actually have to think for a long time and trial and error for a long time, those are usually given and you just work it out. But once you see, guys, this curve C is the source for your x and your y, which is parametrization. Once you have that, the rest is plug and pray, right, that you're going to do it right. So we have r, which is given inside C. You compile r, and then you take its derivative, and then you find the magnitude for the vector, and that's where you got 2t. What is 2t? That's this portion here off of your integral that you're computing. That's 2t. The function that goes into the integral needs to be parametricized in terms of t. As you can see, the function that goes inside the integral is currently not. in terms of t. So we have to make it in terms of t by simply replacing x and y that are given in our parametrization in terms of t's. So now I computed the r prime and everything is ready to be plugged in. We have the integral, we have the limits that are given, we have the function t times the magnitude of r. Now the the function, the temperature function, is given in terms of x and y, which we plug in the parametrization in terms of t. So that's how we got the next line. Those are only x and y plugged in. And then after that, there is some algebra going on that you have to do. And eventually, it's 300 pi. So let's do another example because we can. Now let's go and take a look immediately at the homework, because you know all the letters and you can read the ones that are done in the book. So here is, let's go with number, let's say 18. It says integrate the line integral of xy raised to the 1/3. They could have just put in cube root there. The curve C is the curve y equal x squared from 0 to 1 for x. I try to do this on your own. I'll put the formula one more time on the board so you know it. Integral C f of ds is equal to a to b f x of p y of p times the r prime of p d of p. C is your x of p y. So you have parametrization within C. If you just figure out what plugs in where, you should be able to quickly come up with the answer. Right? Done?
Move forward with NC.
You have what?
Move forward with NC. Wait,
It's a problem. There's minus 2. Where do we begin? Where do we begin? Yes. Parametrization first. You have to parametricize. If you don't parametricize, doomed. Can't do anything. So let's parametricize here. Parameterization. There we go. Parametrization. That's where we begin. So what do I have? I have y equal x squared. So to parametricize this, I can use the dummy parametrization, x equals t, y equals t squared. And then because x is equal to t, I can immediately go 0 less than t less than 1 because there is one-to-one correspondence between the two. So now immediately our r is given as t comma t squared comma 0 less equal than t less equal than 1, and that is our parametrization. I'll box it. Find r prime, find the magnitude of r prime, plug everything in, and be done. The correspondence between x and t is 1-to-1 because x equals to t, so I can just replace x with t, and that's how we got the same thing. Sometimes you want to be t over 2, then you replace t over 2, let's say, and then you multiply by 2 and you get 0 to 2. So it can be anything. Yeah. Yes. Yeah, because it's called a dummy substitution, but that's the cheapest and the easiest of all.
I don't know.
Oh, that's without
Yeah, I know. I was like, wait, she wrote, she said it too.
Yeah, and wrote how.
That's actually really funny. Her and I could go like,
Okay, let's take a look at the solution of this. We gotta keep moving, guys. So, r prime is 1, 2t, and then the magnitude of r prime is going to be the square root of 1 plus 4t squared. You can't do much with this, right? Just leave it. So integral over curve c of xy raised to the 1/3 ds is going to be the integral from 0 to 1, because that's our t limits, from 0 to 1. Now x is t, y is t squared, all of that to 1/3, times the square root of 1 plus 4t squared dt. Now t times t squared is t cubed, and that cancels 1/3. Isn't that awesome? So the whole thing over here is just t, and we have enough for u sub. We don't have to use trig sub, so that helps things along. So u is equal to 1 plus 4t squared. du is equal to 8t dt. We don't have 8, so we make one up. There we go. So 1 over 8. The limits go from 0. So when you change that into u, the 0 changes into 1. And when you plug in 1, you get 4, 5. There we go. What do we have? We have square root of u du. Awesome. So the integral of that's 1/8. Integral of this is going to be 3/2, so 2/3. U to the 3/2 from 1 to 5. These guys cancel to a quarter, so it's 1 over 12. And we have 5 to 3/2 minus 1. That's some kind of decimal number, no one cares. Right? You can get it to arbitrary precision from there. So that is us computing the line integral. Can we have these integrals in a 3D input? Yes. What changes? Nothing. We just toss in the z as another parametrization. So let's take a look at the at the 3D version. So line integral in 3D. Line integral in R3. It's just going to add z to the whole mix. So we still have the same setup. This is the arc length. And then we just compute again from A to B. And now our function is going to be in terms of x of t, y of t, and z of t. Again, times the r prime of t, which is the magnitude, and then dt. I don't have to write the whole exploded version. You know what to do. So for 3D input, you have the same thing. Moving along to the line integral of the vector field. So what are we doing with the line integral in the vector field? Well, we're computing the same thing. I hope you remember that the vector fields can be generated by the gradient of a function. That function is called the potential function. And if you find the gradient, which are partial derivatives, vector of partial derivatives, you get the vector field. So we called it the gradient vector field. So now we can integrate and find the line integral of the vector field. And the way to do that is to find the dot product between the vector field and the dr, which is the change in the direction in which we are moving along the path. So you know that r is the path. That's the function. You can find its derivative for velocity and acceleration again. You can have it as a dr, which would be indefinitely small increments to move along the curve C within a vector field. So what is the definition here? What are we going to use? So we have vector field F is expressed through FGH, which are the functions, each one in respect to t. And then there is a parametrization C that gives us, so C has a parametrization R, that's a vector, is equal to standard x of t, y of t, z of t. And we still have our good old t to be between a and b. So what are we having now? We're going to have the line integral. We represent this as a dot product now because these are all vectors. And you simply just distribute these. So integral a to b of f of times f of t times x prime of t plus g of t times y prime of t plus h of t times z prime of t dt. Are you really going to remember this? Well, I hope you're remembering this one, the vector notation of it, not the exploded one. You have to use exploded one to compute, but the vector equation is the one that it's easy to remember, because you know how to compute the dot product. If your dot product is given as FGH, which are the functions within your vector field, which is what we covered yesterday, and you have R, which is x, y, z, and R prime is going to be x prime, y prime, z prime, then the simple dot product between these two, first into a first, second into second, and third into a third. Now these need to be derivatives. You can see the prime right there. Remembering this equation is much easier, and you can just write this out rather than going and breaking your head to memorize this much information. Again, it's up to you which way you are going to remember the vector field line integral calculation. Now this is a 3D case. In R3, if you want the R2, all you need to do is to throw away H and Z and you have R2 case. So let's immediately do an example for this. Again, the ones that are in your book you can read because you know the letters. I'm just going to do something from homework. Yes? I went up real quick. Now I have to scroll down. Let's compute one of the 2D cases because they're faster. Want another parabola, or let's do one of the line segment problems because I'm sad to say I found some cases where you can't parametricize a line, and then I wept. So here's problem 35. We have the vector field given as y comma x. So that's the vector field. And line C is the segment, or line, segment from 1, 1 to 5, 10. The first order of business is parametrization. So we are supposed to parametricize that line over there. So how do we do that? There are many ways. But first you use 2 points to find the equation of the line, and then you can use those dummy variables again, where x is equal to t, and solve it that way. You can find more exotic ways to do it, but why? So let's go. Deal with parametrization first. So we first have to figure out what is the line here. I have m is equal to 10 minus 1 over 5 minus 1, which is 9 quarters. And then we need to figure out the y-intercept for it. So we have that y, you can use 1, is equal to 9 quarters 1 plus b, from where b is equal to negative 5 quarters. So now we know that the curve C is actually line y equals 9 quarters x minus 5 quarters. Now we also have to make sure that we start at 1 and end at 5/10, so we have to end it somewhere. But first we make a parametrization. X is equal to t, as I said, standard stuff. So if x is equal to t, then y is equal immediately 9 quarters t minus 5 quarters. And since x is equal to t and x goes from 1 to 5, then t must go from 1 to 5. Not always going to be the same, but in this case it was. Now we should check this and make sure that we are getting the correct values. So if I plug in 1 for x, you get 1. For y, you get 5. That's good. No, you get 1, because 9 quarters minus 5 is 4 over 4. Good. If I plug in 5, for the second point I get 5, and then I plug in 5. 5 times 9 is 45, minus 5 is 40 over 410. Perfect. So just to check. So now we have our parametrization. Vector r is given as t, comma, 9 quarters t minus 5 quarters. And t is between 1 and 5. So there's our parametrization. Immediately r prime is 1 comma 9 quarters. And then to find the magnitude of r prime, oh no, wait, we don't need that. We're not dealing with the line integral, we're dealing with the vector field. Oops, sorry. So we have the vector field y comma x, and we have our parametrization. So now remember that the line integral, blessings, the line integral is the dot product between the vector field and the r prime. Yeah, we do need r prime. Why did I erase it? So here I'll do r prime. I'll put it on the side, which is 1 and 9 quarters. We don't need the it's y comma x. So I'll write it here in this form, and then you guys figure it out. So this is y comma x dotted with 1 and 9 quarters dt. So what do? The integral goes from 1 to 5, and now I have the dot product here. The dot product is y times 1 plus 9 quarters x dt, but remember that we actually have x and y to plug in. So 1, 5, what's y? Y is 9 quarters t minus 5 quarters. that's y, plus 9/4, and then x is t, so just 9/4 t dt is equal to integral 1/5. Simplify this, 9 as 18, divide by 2 9/2 t, minus 5/4 dt, and we integrate now. It's calc 1. So integral of 9/2 is 9/4 t squared, minus 5/4 t, from 1 to 5, and that should give us a number. Let's compute, because we can. So 25 times 9 is 250 minus 25, 225 over 4, minus 25 over 4, minus 9/4 plus 5/4. So the first one is 200 divided by 4 is 50. And then this is minus, and then minus 1 should be 49. If everything worked out correctly, it's 49. It's a lot of plugging in, right? A lot of chasing things around. But it's actually very systematic, and you should be able to very quickly catch on what's going on. Vector field is given, and the line is given. That's it. That's the only two pieces of information that you need, because one will give you parametrization, and the other one is the one that you're integrating. So now, parametrization. For most of the time, if this is the one case where you have a straight line and 2 points are given, because they know that you can come up with the equation for the straight line through 2 points. That's 8th grade math. Once you have that line, parametrization can be x equals t, and then y equals exactly the equation, except now x is t. This, because x is equal to t, is going to be the same, because x goes from 1 to 5. Then t will go from 1 to 5, because x is the same as t. Once you have parametrization, you have your x and t. That's immediately your vector r. That will have r prime. The vector formula here for line integral for the vector fields is the dot product between the vector field and the r prime. So now you have the vector field itself. Now, as I said, if you are memorizing the expanded version, you will be automatically here. If you are remembering the dot product, which is much faster, then you write both of those, do the dot product, and then simplify, plug in all the t's in equation. Now, usually, where is the confusion? The confusion is here, because your integral has dt, but your variables are x and y. You have to remember that those variables that are x and y are always addressed here. This is your x, this is your y in terms of t. That is why we need that parametrization. Parametrization, it gives us x in terms of t and y in terms of t. So once you have that, you will be able to compute, because then the whole integral is in terms of t. Whatever kind of witchcraft you have to do that integral, mainly should be used sub or basic, but certain cases, maybe by parts creeps in. You shouldn't be expecting the partial fraction decomposition or anything crazy like that. I mean, are they around? Sure they are, right? But we don't have to go crazy. So now on the board, I'm going to add another formula. And that formula is using the same parametrization. And now the integral of f dotted with r prime dt. So the vector field form. Now, what is it computing? What is it actually computing? Yes? negative 1. What is it computing? It is computing the amount of stuff that you can put through that curtain. You know when you have those see-through curtains that do like that, right? And you put them on the window and you can still light passes through, right? So it's computing the amount of light that goes through, right? That would be a vector field. So all those vectors that are pointing, all the photons that are going through the curtain. So vector field or the line integral is computing the area of that thing if you are just using the line integral, the arc length. All right, let's see what else is the very important stuff. Okay, that's a fancy notation. Work is application. I'm just going to write this out. It's the same thing, so work is equal to the integral of the force times r prime dt. Why? Because wind can push things. Wind is vector field, we talked about it. Electric field, magnetic field, you can make them work for you, right? The electrical motor turns, so it's magnetic field there. Well, electric turned into magnetic, and then magnets repel and turn. All right, now we're getting into computing two concepts that are very important. They're called circulation and flux. I have a very interesting story for flux. For flux. Flux, yeah. One time I was at a restaurant listening to two older guys. I would say one was in late 50s, the other one was in early 60s or so, talking. And one guy said, "Oh man, we just finished interviewing 150 useless graduates." Now that I caught that sentence. That was the first thing I heard, and I was like, I want to hear the rest of the conversation, right? So you kind of lean in a little bit, right? And I'm trying to figure out what's going on, and then I couldn't, so I actually talked to them. Because that, and at that time I was actually working at NGIT. And at that point I wanted to know what does that mean and what were they hiring, because there was definitely some kind of technological field, right? So I talked to the guy. It turns out that one of these guys is a retired AT&T guy, the older one, but the other one was still working, and he was working at a researching facility that Exxon has in Clinton. And he was working as a researcher there. Apparently they were hiring in a research facility, and they interviewed 150 college graduates for the position, and no one apparently got the job. Amongst all the standard interview questions, they asked those people interviewing to compute the flux. That was on the interview. Well, let's see how's that computed in case you ever apply. All right, they might have the same criteria to hire, Yeah, the researching. I mean, they deal with alternative energy research there and all other kind of stuff. Exxon, yeah, they do oil and all of that stuff, but they do much more than that. So, yeah. And I didn't say anything, but I thought it's in Calc 3. So, yeah. Let's see what the flux is. First circulation and then flux. So circulation. Let F be a continuous vector field on the region D in R3. Let C be closed, smooth, oriented curve in D. The circulation is, and then it gives you the definition. So let's go. Let F be a continuous vector field. That's the VF is the vector field. And C, well, in R3, and C be a closed, smooth, oriented curve. In D. The circulation of F on C is the line integral F dot R. They have a different form there, but we know what we're computing, which can also be represented this way. Where T is the unit vector tangent to C, consistent with the orientation, which means remember that all of the parametrization curves are always oriented clockwise or counterclockwise. We call the positive orientation the one that is done in the terms of, in the direction of the increasing parameter. So I have all of this, and then we have T is the unit vector tangent to C. I know this is a lot of words, but it should make sense if I draw a picture. So here's the closed curve. Let's say this is the orientation. So this is your curve C. This is the region D. And then at every point, I can find the tangent vector. And those are all the T's. So what kind of vector field will have a circulation? Tornado is a good example. All right? Now, does the sun produce circulation? No, it's a radial field. There's no rotation there. The sun creates a vector field which shines out, right? So there's no circulation. Circulation is, technically think of it as a rotation along the edge of the sea. If these tangent lines rotate, not everything has circulation. And I just gave you an example of a source, like a sun, that will emit the vector field, which is radial in that case, and it doesn't have circulation to it. Circulation is equal to 0. Flux is going to be maximum there. right? There's no circulation, flux is max. So we'll have to figure those things out. So we are going to take a radial and rotational vector fields, and it should be clear that circulation for radial field is 0 and circulation is going to be a max. And then when we do the flux, we do the same two examples. So I have to do the same two examples as in the textbook because those are the best two examples under the sun. And then homework examples should work the same. So let's take a radial field. Radial field is xy, and on unit circle. So now what's the parametrization? I'm just going to start writing par, which stands for parametrization. Parametrization for unit circle R is just cosine t sine t on 0 to 2 pi, which means that R prime is negative sine t cosine t. And now to compute our integral, we just do the same thing, 0 to 2 pi, we dot those two. So x is cosine t times negative sine t plus, because it's the dot product, y is sine t times the cosine t, everything dt. But you can see the thing over there is 0 because you have negative sine t cosine t plus sine t cosine t. So this thing is 0, you integrate that, you get 0. Circulation on a radial field is 0. Let's take a look at the rotational field. Now rotational field F is given as negative y x. Again, unit circle for our C. Just wanted to check the stream, see it's still going. So we have same parametrization. R is given as cosine t sine t. It should have R in front, but R is 1, so we omit that. Same R prime, negative sine t cosine t. And then what else do we have? Now we immediately plug everything into integral, which is our integral f dotted with r dt, 0 to 2 pi. Okay, now negative y, and y is sine t, so negative sine t times r, which is cosine t. And then we have x, which is cosine t times start from scratch. Yeah. So what do we have? We have f that's negative y. Negative y is the negative sine t times the first one from here is cosine t plus x, which is cosine t, time. No, I'm looking at the wrong one again. You know what? I'm going to circle them because I don't want to make a mistake for a third time. Here's your x, here's your y. All right, let's go again. So negative y is negative sine t. Good. Times the r prime, which is again negative sine t. Good. Plus x is cosine t. There we go. Times another cosine t. dt. Finally. Which is integral 0 to 2 pi of sine squared plus cosine squared, which is 1. And we get 2 pi. Finally. Wow. So we see that we are getting circulation on the rotational field. We are not getting circulation on the radial field. And as soon as I show you these pictures from the textbook, it makes sense. So we have the two images there, radial and then rotational. So you see on the rotational field that it's kind of forcing it to spin, right? It's forcing it to spin. Where this one doesn't experience any spin because this one is canceled by that one, they're all pulled in the same way direction. So that one that does not experience circulation, and this one does. Circling around. Now this is just a quantification. Quantification of what the vector field is doing. Remember that we had the quantification for curvature in chapter 11 at the end, right? We were quantifying of how much the line bends, how much it curves at the spot. Can you compute this for 3D? Sure, just toss in another variable there because these are the dot product between two vectors. You can do this for 6-dimensional space if it makes sense for any application. It doesn't, but you can. Ready for the flux? Apparently 150 people were not. I need the test because I have to add the quizzes. Quizzes are still going on.
Yeah.
One tonight and one tomorrow.
Really?
Mm-hmm. It was 5 before the test.
There's no 5 before
You
this?
can hang out. You can sit and hang out. You can hang out and sit and enjoy the rest of the class, or you can just go home.
Wow.
Whatever.
I haven't eaten since
Me neither.
12. Really?
Oh, that's fine. I'll do it. Now, what's the flux, guys? Nope. It's how much stuff you can fit through the. So you have the C is the curve, which is going to outline certain area. Flux is going to compute how much stuff you can fit through that space perpendicular. And the best way to understand that is going to be the fan. All right? So when you turn the fan on, it starts pushing the air forward, which is making the wind, which is the vector field, right? The bigger the fan, the more stuff passes through. Smaller the fan, less stuff is pushed through. So the fan. Now, what's the circulation on a fan? It's going to be 0. Circulation on the vector field that is produced by a fan is 0. It's very confusing because you are thinking that the blades are spinning. Yes, they are. But I'm not computing anything with blades. I'm looking at the wind, which is the vector field that it produces. it is not creating a turbulent flow. It's producing the vectors that are going forward, like this. If you're talking about, I don't know, something that will create flow like this, what would that be? Shotgun pellets. There you go. In the coils in the barrel, when you fire it off, it's going to make all of them spin. So the whole it goes forward, but they also spin. That's going to be rotational. That one has circulation to it, and the flux. So you have to be careful of what you're producing, right? So the first one, the circulation, had that capital T. T were the tangent vectors. Now this one is going to have vector n, which is the normal vector. So if I hold this as a curve C going like this around the edge of the paper, the flux is going to be all of the electric field, magnetic field, the wind, the fluid flow that can go perpendicular from this surface towards you. That's what the flux is computing. So now we're going to take a look at the formula for it. So as I said, it's going to be the vector field dotted with the normal vector n, because we want to see all of the stuff that is perpendicular coming out of the surface that we are looking at. So we are going to take a look at, again, all of the stuff is the same. The F is the, well, let's write it. F is your vector field, right, which has the F and G in it. What happened? Oh, change the screen. Fine. There it is. Wasn't it much better to see it typed than me scribbling it? So again, we have the continuous vector field on R2. And we have curve C given as R of t equal to x of t. Again, parametrization. Everything is parametricized, guys. Everything. Smooth oriented. And does not intersect itself. That's another important point. So number 8 would not be a good candidate here. So we have the flux is going to be the vector field times all the normal vectors that are pouring out of that surface, computed A to B, and then we have f of t times the y prime of t minus g of t times x prime of t dt. The question is, where is this coming from? Well, you remember that the normal vector involves the dot product, as the cross product, and the cross product, right, goes on and it's computed through the determinant. So this is actually the determinant of the non-zero part of the dot product, because one of those coefficients are going to be 0. Again, derivation of this, because not the honors section, don't worry about it. You can look at it. Look at it in the book. But the previous one was the straightforward dot product for circulation, and this is the cross product. So we are using the determinant of the matrix, which means it will have the minus sign there, and they're mixed. As you can see, it's not f with x. So circulation is f times x plus g times y. Over here you have f with the derivative of y minus. So they're switched. And now if we compute this for the same fields, you will see that they completely swap their spots. The rotational one will have a flux of 0 because all of the stuff is circulating, where the other one is going to have the maximum. So let's go. Radial field. So what's the radial field? Again, it's radial field is x, y. Again, unit circle. So we have that r is again cosine t sine t. R prime is negative sine t cosine t on 0 to 2 pi. Again. And now all we need to do is to plug everything in. So the flux here is going to be integral from 0 to 2 pi. And then we have function f, which is x, which is cosine t. What happened? No, just r prime. Normality comes from the cross product, not from... And y prime, so that's going to be another cosine t minus g of t, which is y, which is sine t, times another sine, negative sine t, dt. You can see that the thing again inside is 1 because it's the Pythagorean. And you have, well, you have 2 pi, right? Because integral of 1 dt is just t from 0 to 2 pi, and we get 2 pi. So flux for the radial field is 2 pi. Rotational? Negative y comma x. Again, unit circle and all that stuff. So what we have for flux? Again, 0 to 2 pi. And now you're going to have f, which is negative y, which is minus sine t times cosine t minus cosine t minus sine t dt, and 0 because this part over here is 0. So now you see that the rotational fields have a 0 flux and the radial field has a maximum.
So basically you plug in the R and R prime in.
Yes. It's the same spiel because you are doing the cross product between two values. What do you mean formula is wrong? You just wrote it wrong. Oh. That's a... All right. Actually, wait. It is a dot product there because it's ds. It's the arc length.
So how do you get the minus?
No, this is a normal vector. You get the normal vector from the cross product. Cross product between r and the tangent vector t. So, okay, so here I'll try to. So here, take the point like this. This is your vector r. This is your vector t, and then perpendicular to those is the vector n. So you get n is the r cross t. That's where you get your vector n. And then you dot vector n with the function to get the flux. And that's it for this. Now we are going to call these later on, the divergence piece and so on, but we'll have to get there. So let's go for the break. When we come back, we'll take care of the next section, which is conservative vector fields. We're going to have a name. We're going to give this a name, this formula and so on. So we'll get there. So we'll resume. I'll have to restart the stream for the next section, so it's new title.